Most of the electricity powering our modern world starts with a very old concept: setting things on fire. This multi-step process of burning fuel to create heat to spin a turbine is strictly capped by the laws of thermodynamics, specifically something called the Carnot efficiency limit. And naturally, it guarantees a massive amount of exhaust and pollution. Batteries offer a clean alternative, but a battery is just a storage container. Once it consumes its internal chemical reactants, it dies, and you have to plug it back in. But what if you could build a device that converts chemical energy directly into electricity, like a battery, but theoretically never dies as long as you feed it fuel? Bypassing the fire provides a direct path to scalable, continuous, and completely clean power generation. This is the core premise of the fuel cell. This diagram illustrates the core building block, a single unit cell structured around a three-phase interface. Pure hydrogen enters the anode, while oxygen is fed into the cathode. The reaction forces electrons through an external circuit, creating usable power, while ions cross the central electrolyte. Because nothing is actually burning, there is no smoke, smog, or ash. The only byproducts leaving this system are pure water and waste heat. A single isolated cell like that produces a very small amount of voltage. To generate usable power, engineers have to link multiple cells together in a series to build what's known as a stack. This exploded view breaks down a planar bipolar stack design. Flat unit cells are sandwiched between separator plates, which act as physical gas barriers while using built-in channels to evenly distribute the flow of fuel and air. This schematic compares different cell geometries. By wrapping the current tangentially around a tubular cell, engineers can create a much tighter seal for the gases and significantly boost the structural integrity of the hardware. Stacking is the critical architectural step. It takes a fragile, microscopic chemical reaction and scales it up into a rugged, industrial power block. But even the most robust stack can't survive on a bare table. It requires a dedicated life support system, known as the balance of plant. This power plant illustration maps out those external systems. On the left, fuel processors reform natural gas into pure hydrogen, while air blowers keep the stack fed. On the right, power conditioners smooth raw DC voltage into regulated AC grid power. The balance of plant is what ultimately transforms an isolated scientific component into a self-sustaining, commercially viable power station. The defining feature of any fuel cell comes down to just one choice: the electrolyte. That single material dictates the operating temperature, the hardware design, and the overall efficiency of the entire system. This diagram of a polymer electrolyte fuel cell highlights a low-temperature design. By utilizing a solid polymer membrane, these cells fire up very quickly, making them highly attractive for mobile applications like cars or portable electronics. But low-temperature systems carry a critical vulnerability. Their platinum catalysts are incredibly sensitive to carbon monoxide poisoning. If the fuel isn't strictly purified, the catalyst degrades and the cell shuts down. That strict chemical diet makes them ideal for enclosed, portable tech, but difficult to integrate into the messy realities of our heavy industrial infrastructure. For heavy industry, engineers rely on high-temperature cells. Looking at this table, molten carbonate and solid oxide cells run between 650 and 1,000 degrees. This heat eliminates expensive metal catalysts and allows the cell to internally break down dirty fuels directly inside the stack. Facilities can even capture that extreme waste heat for industrial cogeneration, driving the total system efficiency well past 60%. The fuel cell is a versatile architectural framework, capable of cleanly powering everything from a single vehicle to a massive city grid, simply by swapping out the chemical core.